Hello all, my name is Rahman and welcome back to my YouTube channel. So guys, in this video we are going to talk about the concept of kernels in support vector machine learning. So guys, where we left off in the last video, we were talking about the visualization and prediction in the last video, and before that video we have talked about the optimization problem in support vector machine. There we have implemented the optimization in the Python, and before that one video we have talked about the building support vector machine from the scratch. So guys, these three videos are related and these videos will be given in the description below, and the code used in these videos also will be given in the description below, so you can go there and copy the code. So guys, in this video I am going to talk about the kernels in support vector machine in machine learning. So guys, first of all we have a question that what are kernels and why they are used. So guys, for both of these questions we have the same answer, and that is kernel is used due to a set of mathematical functions used in support vector machine, providing the window to manipulate the data. So the kernel function generally transforms the training set of data so that a non-linear decision surface is able to transform to a linear equation in a high number of dimension spaces. Now guys, we have the same answer for these two questions, but guys, we have the another question, and that is why do we use the kernels in machine learning. So before this I have given the answer of why do we use the kernels in support vector machine and what are they. Right now guys, we have the same definition, but guys in a different way, which will be explaining you in a clear way. So guys, kernels in machine learning is used to address the non-linearity present in the data set. A user specified kernel function similarly function adds another dimension to the dataset. By doing this, dataset can be classified using a linear hyperplane. Now guys, we have another question, and this is completely different, and that is what is the purpose? What's the purpose of using the kernel method? So guys, kernel method use the kernels or basis functions, like we have used some videos before, like we have given something like x sub I x into w plus b. So guys, b is a base, right? So guys, kernel method use kernels or base functions to map the input data into a different space. After this mapping, simple models can be trained on the new feature space instead of input space, which can result in an increase in the performance of the models. Now guys, let's go ahead and get started. So guys, if you remember guys, some videos before we have used it, what we say, I'm going to show you that here. We have used a graph something like this, right? We were having something like this, where we were having the x2 and x1. So guys, I'm just giving this roughly. Okay, here now, first of all guys, here this is x1. Now guys, you are having some of the positives and some negatives, something like this. If I show you plus, and here also we are having minus, again a plus here, a minus, and then we are having a plus, and again we are having a minus and plus. Okay, something like this, right? So guys, if you remember some videos before, we have used something like this data set in the beginning of the support vector, on the topic of support vector machine in beginning. Okay, so guys, in the very beginning of the topic of support vector machine, our question about whether or not you could choose an SVM data, something like this that you are seeing on the screen. At least we know that. We know so far, is it possible or not? No guys, this is not possible. It's not, at least not like this. One option however is to take a new perspective. One thing you can do is by adding a new dimension. Okay, for example, if you see here this data, we could add a 3 dimension using some sort of function. Like for example, if I show you, like for example, we can use here something like x3 equals to some sort of function, something like this, like x3 equals to x1 into x2, right? Now guys, for example, I'm going to show you again, and it should be something like this, x3 equals to, and then we are going to multiply this with the x1 into. So guys, here I am not going to use the multiplication symbol. I am going to use something like this symbol, computer multiplication symbol, because if I give something like x, then it's going to be confused, right? So anyway guys, now we are going to multiply the x3 equals to x1 into x2. So guys, let's say let's say that we have the 3, not 3. Okay, so anyway guys, we have 3. So as I said you, we can use this some sort of function, something like this, something like x3 equals to x1 into x2. So guys, this might work here, but it may not. So guys, we have some chances. So guys, there is a probability of this one, right? It might work or it might not work, right? Also, what about in the cases with image analysis? Like for example, while we are doing the image analysis, where you might have hundreds or more dimensions, right? It's already the case that performs in an issue. So guys, this is a probability that it may work or it may not work. So guys, here we have some chances. And guys, you should know that add a bunch of more dimensions to the data is already highly dimensional, right? So guys, we are only going to further significantly slow the things down. Now guys, what if I told you that you could do the calculations in a possibly infinite dimensions, right? So guys, it turns out that we actually can do this with the kernels, right? Now guys, what the kernels do allow us to do is working in many dimensions, like I said it before. So kernels allow us to do work in the many dimensions as possibly as we can. Now, without actually paying the process costs to do it, kernels do have a requirement. They rely on the inner products. For the purpose of this tutorial, dot product and the inner product are the entire interchangeable. So guys, what we need to do is, in order to verify whether or not you can get away using kernels, is confirm that every interaction with our feature space is an inner product. Okay, so guys, first of all, we will start at the end and work our way to confirm this. So guys, first of all, let's draw. If you remember guys, some videos before, we have used a formula something like, we have used that in the code something like y equals to sine w vector w into x vector x plus b, right? So if I show you that, something like y equals, and then it's going to be sine, and then guys, in the brackets it should be vector w into x plus b, vector x plus b. So guys, as you can see here on the screen, so guys, this is a formula that we have used. Now guys, we have a question that, first of all, how did we determine the classification of a feature set after the training, right? Is this an interaction or an inner product? So guys, we have this question that, is this an interaction or an inner product, right? So guys, we can interchange vector x with the vector z. If I show you here, with the vector, we can interchange the vector w, vector x with the vector z, something like this, right? Now guys, moving along with the revisit of our constraints, if I show you, like we were having y sub I into x sub I into w plus b equals -1 greater than or equal to 0, something like, if I show you again, y sub I, and then we have the x sub I, and then I'm going to multiply this, let's give it as the dot, and then we have the w plus b, and guys, -1 greater than or equal to, let's give it as to 0, right? Now guys, here, how about here, right? If you remember guys, some videos before, we have divided these constraints like y sub I into x sub I into w plus b -1 greater than or equal to 0. Now guys, how about that here? Is this the interaction or interaction or an inner product, right? So guys, we have this question again that, so guys, if we recall that y sub I into x sub I into w plus b -1 greater than or equal to 0, as I said you, is identical to y sub I into x sub I into w plus b equals to greater than or equal to 1, right? Now guys, so here we can easily replace our x sub I value with our new z sub I, right? Like for example, instead of this x sub I value like this, if I give, and then we can give it as value with our new z sub I, like for example, if I show you z sub I. So guys, we can say that it is said that x sub I is equals to z sub I. Now guys, I'm going to clear off all of these things. Now, first of all guys, what about the other formal optimization equation for the w, right? We have also this question, right? So I'm also going to talk about that. For example, if I am going to show you with the w, and then it's going to be equal to then sum I'm going to give, and then sum of alpha sub I and alpha sub I into y sub I. Let's give it as y sub I, and then I'm going to multiply this with the x sub I. So guys, here we have, if you see, now guys, there is yet another dot product, and it's also called as inner product here. So guys, we have another dot product, or you could say it as inner product, as I said you, and we have any other equations. Are you having those things or not? Alright, so guys, we are not having those any other equations. So guys, how about that? How do we do that? Right, so guys, recall the equation like Lagrangian, right, where we have the Lagrangian equals to sum of alpha sub I minus 1 by 2 alpha sum of I sub I, and then we have the j sub j alpha I. I'm going to show you that on the after writing on the board. So guys, as you can see here on the screen, this is the Lagrangian formula from the time I was talking about. So guys, this is L equals to sum of alpha sub I minus 1 by 2, and then we have the sum of I and j, and we have the alpha sub I into alpha sub j, y sub I into y sub j, into, we are multiplying this with the I sub x sub I into x sub j. Now guys, I have some videos before I have talked about the Lagrangian function, like what is Lagrangian, and I have talked about that in the video of constraint optimization with the support vector machine. So guys, first of all, I'm going to talk about what is Lagrangian again. So guys, this function L is known as the Lagrangian. Okay. So guys, finding and solving for the gradient of the Lagrangian means finding the points where the gradient of A and B are parallels. So guys, here I said that points where the gradient of A and B are parallels. So I have just given an example of A and B. So I have talked about that what is Lagrangian. Now guys, why we use Lagrangian, and what is Lagrangian used for, and what is Lagrangian in machine learning. So guys, we have two things right now. So guys, this is the series of machine learning with Python, right? Now support vector, we are also talking about the support vector machine, right? So guys, here support vector machine is an algorithm. So we don't need to confuse the difference between the machine learning and the support vector machine. So I am going to talk about what is Lagrangian in machine learning. So guys, the method of Lagrange multipliers is a powerful technique for constraint optimization. So if you remember some videos before, we have talked about the constraint optimization with the support vector machine, where we have used the Lagrangian function here. So guys, this is why I have used, and while it has applications for far beyond the machine learning, it was originally developed to solve the physics equations in the machine learning. It's used for several key derivations in the machine learning. Now guys, why we use Lagrange multipliers in the support vector machine, right? The SVM optimization problem can be solved with Lagrange multipliers. So guys, if you remember some videos where we were having a problem of the support vector machine optimization, right? So the Lagrangian function can solve the problem of support vector machine optimization. This technique can be used to transform the constraint optimization problem into a formulation whose solution is equivalent. Okay. Now guys, what is the Lagrangian used for? Right? As I said before, Lagrangian function, also called as Lagrangian quantity that characterize the states of the physical system. So anyway guys, let's stop talking about the Lagrangian function. Now guys, I am going to talk about how to handle, like in the starting of this video I have talked about why we use kernels like that. Now I am going to talk about how to handle for the non-linearly separatable data. Right? I am going to talk about that right now. So from the time we are talking about the introduction, I have just given the introduction to support vector introduction to kernels just now. Now I am going to talk about the main concept is talking about how to handle for the non-linearly separatable data. Now so guys, I am going to talk about how to handle for non-linearly separatable data. So guys, as we learned some time before, we can utilize a kernel to help us translate our data to a plausibly infinite number of dimensions in order to find one that has linear separability, right? And we also learned that the kernels can let us go out of these dimensions without actually paying the cost of for these higher dimensions. Now guys, generally kernels, now we have a question that how will be the kernels defined as, like, right? Now guys, generally the kernels are defined something like k. Okay, so k means kernel here we have, and then in the brackets we have to give here something like x, comma, you have to give again x. Okay, so guys, generally the kernels are defined in this way, but guys, we have this x and x 2 times, but here this x is going to be different, something like it's going to give us something slash something like this. It's going to be power 1, let's say. Okay, so we can also call it as x prime. Now guys, the kernel function is applied to x and x prime. So guys, this is known as x prime, I'm going to call it. And then this will be equal to the inner product of z prime of the z and z prime. Like for example, if you see, it's going to be inner product of the z. Okay, so guys, let's call it as multiplication, and then this is known as z prime. Let's give. Okay, now where the z values are from the dimension of our new dimension space. So guys, if you remember, in the last video I have talked about the z prime, or not z prime, I have talked about I'm going to replacing that with this line, right? So sometime before I have talked about how I'm going to replace the z, I'm going to replace the x with the z, something like that. So that's why I'm saying it as our new dimension space. Now we have the x, okay, and we have this, now we have the k kernel, and then we have the x comma x prime, and we have the equals to z into z prime. Now guys, the z values are the result of the sum function x. Okay, so guys, and these z values are dotted together to give us the kernel functional results. Like for example, I'm going to clear all of these things, and then let's say it as the k again. Okay, now let's say it as k. Okay, and then guys, in the brackets I'm going to give something like x. Okay, and then it's going to be x prime, something like slash, and then it's going to be equal to z, and then it's going to be multiplied with the z prime. Okay, now guys, let's say this is something like this. Now guys, we have what are the z values are the result of some function x. Let's say these are the results of some function x. Okay, so guys, let's say these the z values are the results of some function x, and these values are dotted together to give us the kernel function result. Okay, so guys, this is why we have given something like k x into x prime equals to z into z prime. Now guys, we still have not cover how these saves us any processing, right? So guys, now I'm going to also talk about how to handle for the non-linearly separatable data, and then I'm going to talk about the processing here, how to do the processing, etc. So guys, in this video I'm not going to implement this with the Python. I'm going to just show you the examples here on the board. Now, so guys, let's do here the processing, for example. Okay, so now I'm going to take here an example. So first of all, let's clear all of this one, and then I'm going to start with the polynomial kernel here, and we have compared the requirements of a polynomial kernel to simply taking our current vector and creating a second polynomial from it. Okay, so guys, first of all, let's create the kernel here, polynomial kernel. So guys, for creating, I am going to use here the x. Okay, and then guys, x is going to be list something like this, and we have the x comma x1, and let's give it as x2. Okay, and then we have this, what we say, we have this x equal to this one. Now guys, what I have to do here is we have to convert this into a z, right? Z space, right? Now guys, let's use it the z, and we have the z equals, I'm going to use something like this, and then we have the 1 beside this 1 comma x. I'm going to give 1 comma x1. Let's wait. Okay, now 1 comma x1, and we have the x2 again, comma, and we have the x2, and guys, you will be confusing for instead of 1, and so guys, this is also comma, and this is also comma. This is the 2 I have done. This is also comma. Now I am going to write the x2, and guys, with that we have to do the x power 2. right? So let's make here some dot. So guys, let's assume it as the dot, and then we are going to do it as the x power 2 and x sub 2, something like this. This is also 2 and these are also 2. Now guys, beside this one, I'm going to use the x comma 1 x2. Now let's give it as x comma. So guys, as you can see here, this is the formula. But guys, we have converted this to it. Now guys, it's confusing for us right now, right? So guys, I'm going to clear all of these things and rewrite it after pausing the video. Now guys, as you can see here on the screen, we have the z equals to, I have written that sometime before. Now it's clearly we have the 1 comma x1 comma x2 comma x1 square comma we have the x2 square, and then we have the again and then we have the x1 comma x2. Okay, now guys, now you will be confusing with the x. We have the x equals to x1 comma x2. So sometime before we were giving something like k, and then in the brackets we were giving x1 comma x prime, something like this. So guys, we will also write that one also. So let's write that here, and that is k. Okay, let's give it as k, and then it's going to be x comma x prime, let's say. So guys, this is known as prime. Now guys, here we can see here we have the k x into x comma x prime. So guys, you will be confused with this because a lot of people will give that in a different way, like they will give that something like x1 x2, and they will also give something like x comma y, or they can give something like this as I have given. So I have just given the same thing, but I have done the different for the x. So guys, I'm going to call it as x prime. Now guys, how we are going to do that equals in the z prime? Like sometime before, if you remember, we have talked about we have given something like k into x comma x prime equals to, and then it's going to be equals to z comma z into z prime, right? So guys, we said that. Now I am going to clear all of these things first of all. Now so guys, as you can see here, I have cleared all of these things right now. So anyway guys, for x comma x prime, let's type it here in this small here. This is x, and the guys in the brackets, I'm going to give here x comma x prime. Let's give something like this. Now guys, we have this one. So guys, for z equals to, we have this one, but guys, for what for z prime, right? So guys, for that also I'm going to give something like z prime, and then in the brackets I'm going to give something like 1 again comma x2 x1, sorry, and then x1 prime. This is prime, and then we have the x2 prime again, and then we have the what we say x2 prime. We have now x1 squared, and with that we have also prime. And guys, same thing for again, we also have the prime for 1, and sorry, this is 2. Let's call it as 2, and then this is going to be squared also, and then guys, this is also squared here, and then it's going to be x1 something like comma x1 is also prime, x1 prime comma x2 is also prime. So guys, for the z prime, we are going to give something like this, and just for the z, we are going to give 1 comma, and guys, the difference is no much that. So guys, these two are different, but guys, at the top of it, we are just adding here we are adding here the slash, which is we are calling it as the prime. Now, so guys, you might have got a question that what is going to be x k kernels, and then in the brackets x comma x prime equals to z dot z into z prime. Then what is it's going to be? What's the output, right? So guys, for doing, I'm going to clear all of these things, and then I'm going to explain you with the example. Okay, so guys, let's say, wait, okay, now let's say that we have the k, let's give it as k, and then guys, in the brackets I'm going to give here x comma x prime, sorry, something like this one, and then it's going to be equal to z into z prime, and then it's going to equals to, right? So guys, you have this question what it is. So guys, we have simplified the problem of x comma x prime, which is equal to z comma z into z prime, right? So guys, we have simplified this one. Now we have the question for what is the z dot z prime equals to, right? So guys, for solving this one, I am going to wait. Now let's call it as 1 first of all, 1, and then we have the plus with that. And guys, we have the plus. We are going to do this as x1, something like this. And then we have the x1, okay, and x1 x prime. This is the x prime, okay. And then we are going to do the again plus, and then guys, it's going to be again x2 into, okay, x2, okay. Now we have the x2. Now we are going to get x2 1 prime, and then we are going to do the plus again. So guys, this is going to be a longer formula here. So I'm going to pause here the video, and then I'm going to explain you. I'm going to write all of these things, and then you are going to be understandable. So I'm not going to waste the time on the video. Now guys, as you can see here on the screen, we have the k into, and then we have the x comma x prime equals to z into z prime equals to. So guys, this is the answer, which is 1 plus, and then we have the x1 into x1 prime plus x2 into x2 prime plus x1 square, then we have the into x1 square, then we have the prime, and then we have the plus again, then we have the x square, x2 x square, and then we have the x2 square prime, and then we have the x1 into x1 prime, and then we have the x2 into x2 prime. Okay, so anyway guys, this is something like this. Now guys, so all of that was manually working through a similar operation that the polynomial kernel is going to do here. So guys, luckily for us, we have starting the dimensions where we have the only 2. Now let's consider the polynomial kernel. So guys, before considering that one, I am going to talk about this one. So guys, we got the solution here for the k into x comma x prime equals to z comma z into z prime equals to. So guys, here we got this one, but guys, this is a little bit confusing for us, but guys, if you understand it properly, then it's going to be easy for us. Now guys, let's consider the polynomial kernel. So I am going to clear all of these things here first of all, and then now I am going to write here something like k, and then I am going to give it in the brackets kx comma x prime. This is the x prime, not x1. And then guys, it's going to be equals to, and then it's going to be plus 1 plus x into xp, right? So guys, just notice here right away that there are no z's mentioned here, right? So from that now we're talking about the z prime, z into z prime, something like that. But guys, here we have not mentioned the z, because this entire kernel is calculated using only the x space. So from the time we're using the z space, now we are going to use the x space. All you need to know here is the calculating using n number of dimensions and p for the power you want to use. So guys, as here I have used, you can see here we have the p, which is the power that we can use here. Like for example, I can use 1 plus x into x into this is the x prime. Okay, this is the x prime. Now I can give something like 1 plus x into x prime whole power 1, or I can give whole power 10, anything I want. But here I have just given because I want to give here the power. I want to choose here the power. Now guys, if you calculate this all out, now our new vectors which will correspond to the z space vectors would be, wait, I am going to show you how it's going to be. Let's show you here. X, we have the 1, and then we are going to do the plus x comma x1 prime, we have the 1, and then we are going to do this plus, and then let's give something like that. Now we have the xn, let's call it as xn prime, and then we are going to give the whole power of p, something like this. So guys, that's what I want to say. Like if I were to give something like, you have to give it the power like 1 plus x comma, and then we have the x1 into x1 prime plus dot dash I have given, then it's going to be n number of dimensions, as I said you before right now. Now guys, as I said you, if we calculate this all out, then our new vectors which correspond to the z space vectors would be something like 1 comma x2, okay, 1 comma x square, and then this is going to be comma, and this is 1, this is 1, and this is going to be comma. Now we have this one. With this one, I'm going to give you something like x2 square, and this is comma, and then we have the root 2x. Okay, and then guys, I'm going to give it the comma, and then I'm going to give it the 2 again, and then we are going to get the x2 here again, x and comma again, we have the root of 2, and then we have the x dot x2. Right, so guys, as I said you, if we calculate all of these things, then our new vectors correspond to the z space. Vectors would be something like this, like 1 comma, you have the x1 square, comma x square, x2 square, then we have the comma again, then we have the root 2x, comma root 2x square, then we have the x2, and then we have the root 2x into x2. Right? So guys, that said, you never go to out that far. Okay, so guys, we don't need all of these things right now, so I have just shown you simply. Now guys, you simply stick with the polynomial kernel here, which is going to simply return the dot product for you, inner product we could say, without you needing to actually calculate the vectors, can take then take a very large dot product. Now guys, there are few kernels, but the only one I will show you here is the radial basics function. So guys, the one thing I didn't tell you about is types of kernels. Now guys, there are other lot of types of kernels here, like for example polynomial kernel, you have the RBF kernel and sigmoid kernel, and a lot of kernels in support vector machines. So we don't need those kernels right now. So anyway guys, that's all for this video. I hope you liked this video, enjoyed watching this video, and I will see you in the next tutorial. Thanks for watching. Thank you. Bye bye.